For as long as we have gazed up at the night sky, Mars has captured our imagination. The dream of setting foot on Mars represents the next great leap for humanity. We have sent robotic emissaries to Mars, our eyes and hands on another world. These missions have transformed our understanding of the planet. A human mission to Mars is an undertaking of unprecedented complexity. It requires the technology to travel millions of kilometers and the means to survive on a world so different from our own. At the heart of this planning lies one fundamental question: where do we land? Finding the perfect spot is the first step in turning the dream of walking on Mars into a reality. Mars is a world of stark contrasts, a planet of stunning extremes. It is home to Olympus Mons, the largest volcano in our solar system. It also boasts Valles Marineris. Yet Mars today is an incredibly hostile environment. Its atmosphere is thin, offering little protection from the sun's harsh radiation. This leads to dramatic temperature swings. The planet is famous for its colossal dust storms. We must choose a location that mitigates these dangers as much as possible because the safety of the astronauts is the highest priority. The perfect site must be a haven in a hostile land. Selecting a landing site for a human mission is meticulous and high stakes. It begins with orbiters mapping the surface in detail. Satellites act as scouts. They use advanced instruments, including high-resolution cameras. This allows scientists to create detailed maps. From this, scientists identify regions of interest. The primary concern is always safety. The landing zone must be flat and smooth. Scientists analyze potential sites with precision. They look for resources vital for sustaining a human presence. The most critical resource is water, locked away as subsurface ice. Astronauts could harvest it to produce drinking water and rocket propellant. This search is a collaborative effort. Each site is ranked based on engineering constraints and scientific potential. It's a quest to find that one perfect spot. A leading candidate has emerged, AP-8. Our search for the perfect Martian home begins in the vast northern lowlands. Unlike dramatic canyons, the northern lowlands offer a more subtle beauty. For mission planners, this vast flatness represents safety for landing. One compelling region is Amazonas Planitia, one of the smoothest surfaces on the planet. It's a relatively pristine terrain, which is exactly what our landing engineers are looking for. We must ensure they can get there in one piece. Discarding the dangerous and highlighting the promising, Amazonas Planitia passes this first crucial test. Amazonas Planitia is more than just a flat place to land. It holds a unique position in the story of Mars. Its surface is thought to be one of the youngest on the planet, formed by vast lava flows that erupted from the nearby volcanic regions of Tharsis and Elysium. These ancient flows paved over the older cratered terrain, creating the incredibly smooth surface we see today. This geological youth is fascinating for scientists. It means that the rocks and soil in this region could preserve a more recent record of Martian history, a chapter of the planet's life that we have yet to read in detail. It's a place where the planet's more modern secrets might be waiting just below the surface. The climate in this region also makes it a compelling candidate. Amazonas Planitia lies in the mid-latitudes of Mars, not too close to the poles and not right on the equator. This positioning offers a kind of Goldilocks zone in terms of temperature and solar energy. It avoids the extreme, relentless cold of the polar regions, where winter darkness could last for months. At the same time, it is far enough from the equator to make the presence of subsurface water ice a real possibility. This balance is critical. We need enough sunlight to power our habitats and rovers, but we also want to be in a location where the precious resource of water might have been preserved from the sun's heat. One of the most exciting promises of Amazonas Planitia is hidden from view, buried beneath the red dust. Radar data from orbiters like the Mars Reconnaissance Orbiter has given us tantalizing hints of what lies beneath. These instruments can send signals that penetrate the ground, bouncing off different layers of material below. In several parts of Amazonas Planitia, the radar has detected a strong signal consistent with thick deposits of water ice. This isn't just a small patch of frost. Scientists believe there could be vast sheet-like layers of ice, meters thick, buried just a few meters below the surface. This is the resource jackpot that mission planners dream of finding. This combination of features, a smooth, flat surface for a safe landing, a relatively young geology for unique scientific study, a moderate climate, and most importantly, strong evidence for accessible subsurface water ice, makes Amazonas Planitia stand out. It ticks almost all the major boxes on our landing site checklist. It is a region that offers a balance between engineering safety and scientific reward. It represents a place where human explorers could not only land safely, but also potentially live off the land, using the resources around them to build a sustainable presence. The promise of Amazonas Planitia has turned it into a focal point for the next stage of our search. With Amazonas Planitia chosen, the search narrowed to finding the safest, most resource-rich spot in this vast Martian plain. Scientists used high-rise images to map every boulder crater and slope, seeking a landing zone as smooth as a parking lot. NASA's exploration zones, 100 kilometers wide, require a flat, hazard-free ellipse for landing, plus nearby scientific targets and accessible resources. Radar data was overlaid with surface maps to pinpoint where safe terrain and subsurface ice overlapped. The goal, a site where astronauts could land safely and quickly access water ice for survival. By layering data, elevation, rocks, chemistry, and radar, researchers identified a handful of elite candidate sites. Through this meticulous process, the best options in Amazonas Planitia finally emerged. After years of analysis, one site stood out, AP-8. Exceptionally flat and smooth, AP-8 sits atop one of the strongest radar signals for subsurface water ice in Mars' mid-latitudes. Here, astronauts could land safely and access water just meters below the surface. No trade-off between safety and resources. This proximity simplifies base operations and makes long-term human presence far more feasible. AP-8 shifts Mars planning from vague regions to a precise, promising destination. While other sites remain under consideration, AP-8 sets a new benchmark. With AP-8, the dream of walking on Mars feels closer than ever. Landing on Mars is the most dangerous phase. NASA calls it the 7 minutes of terror. The spacecraft must autonomously execute a flawless sequence: heat shield, parachute, retro rockets, all while racing through the thin Martian atmosphere. There's no real-time help from Earth. By the time we get the signal, it's already over. With a human crew, the stakes skyrocket. Heavier landers, tighter margins, and zero room for error. The landing site's flatness and safety are critical. Automated systems must trust what they see below. Rugged terrain means last-second, risky adjustments. By choosing AP-8's smooth plane, we maximize the odds of a safe arrival. The right site turns terror into triumph. For engineers, flat means more than no mountains. It's about level ground under every landing leg. Even a slight slope risks tipping a house-sized lander. Using orbital data, scientists map slopes to find vast, consistently level areas. AP-8 is among the flattest spots on Mars, giving landers a large, safe target. Flatness also matters for building a base. Habitats, labs, and power systems all need stable ground. A flat site simplifies rover travel, reduces risk, and speeds up operations. NASA's choice of AP-8 isn't just about landing, it's about long-term safety and efficiency. Flat terrain is the foundation for Mars exploration. A safe landing site must be more than flat. It must be free from hidden hazards. AP-8 excels. High-res images show few rocks or boulders, thanks to a dust layer that smooths the surface. This makes landing and base setup safer and easier for both crew and equipment. The ground beneath is likely solid volcanic rock or ice-cemented soil, providing a stable foundation. Radar data confirms strong, load-bearing ground, no risk of sinking or shifting. AP-8's location also avoids Mars' worst dust storm regions, offering a more predictable climate. While no site is immune to storms, AP-8's conditions minimize risk. Smooth terrain, solid ground, and a calmer climate make AP-8 Mars' safest harbor. A safe landing site defines the entire experience of living and working on Mars. Flat, stable ground becomes the foundation for their new home. On level ground, deploying the habitat is straightforward. Solar arrays can capture the maximum amount of solar energy. A flat landscape makes EVAs significantly safer. This allows the crew to focus on science and exploration. The flat terrain allows easy deployment of scientific instruments. AP-8 provides the ideal laboratory for experiments in off-world living. It's an investment in the long-term success of human exploration of Mars. The genius of selecting a site like AP-8 lies hidden just beneath its dusty red surface. Scientists theorize that water ice could be buried in the Martian mid-latitudes. The Sharad instrument, a ground-penetrating radar, has really revolutionized our search. At AP-8, the radar data returned a signal so clear and strong it was unmistakable. The data shows a vast, continuous layer just a few meters below the surface. On Earth, the only common material that behaves this way is massive pure water ice. This is the hidden treasure we have been searching for. It is a vast frozen reservoir waiting to be tapped by the first human explorers. The subsurface ice at AP-8 is the single most valuable in-situ resource we could hope to find. By choosing a landing site directly on top of this frozen treasure, we fundamentally change the equation of Mars exploration. For the first astronauts on Mars, access to water will be the absolute difference between life and death. Humans need water to drink, to rehydrate food, and for basic hygiene. While a mission could carry a limited supply and recycle it with incredible efficiency, a truly sustainable presence requires a large local source. The ice buried beneath AP-8 represents a virtually limitless supply of fresh water. The first crew's tasks would involve drilling through the few meters of overlying soil, a process well within our current technological capabilities. They would then drill into the ice sheet, heating and melting the core samples they extract to produce pure, clean liquid water. This is the most direct and vital application of ISRU. This local water source would transform the Martian habitat from a temporary shelter into a long-term home. With an abundant supply of water, astronauts could not only drink freely, but also cultivate plants in a greenhouse. Growing fresh food, such as lettuce and tomatoes, would provide essential nutrients and a psychological boost for a crew living millions of kilometers from Earth. The water could also be used for radiation shielding. Water is excellent at absorbing dangerous cosmic rays, and the walls of the habitat could be lined with bladders filled with water from the ice sheet, creating a natural and effective storm shelter to protect the crew during solar flares. The ice itself becomes a building material for survival. Beyond the habitat, water is essential for exploration. The astronauts will conduct numerous EVAs, or spacewalks, to explore the surrounding landscape and conduct science. These activities are physically demanding, and the life support systems in the spacesuits use water for cooling to prevent the astronaut from overheating. Having a plentiful source to replenish the suit's water tanks means the crew can conduct longer and more frequent excursions. It increases their productivity and the scientific return of the mission. It gives them the freedom to venture further from the habitat, knowing they have the resources to support their activities without depleting the critical drinking water supply. Water enables the very work they were sent to Mars to do. The psychological impact of having a vast, accessible reservoir of water should also not be underestimated. Living on Mars will be an experience of extreme isolation and resource constraint. The knowledge that a fundamental element for life is available in abundance, right under their feet, would provide an incredible sense of security and confidence. It changes the mindset from one of scarcity to one of potential. It is the difference between camping for a few weeks and building a settlement. The water at AP-8 is more than just H2O molecules. It is the elixir that makes a permanent human presence on Mars not just possible but practical. While water is, absolutely essential for drinking, the ice at AP-8 actually holds the key to another critical resource: breathable air. The Martian atmosphere is 96% carbon dioxide, a gas that's, toxic to humans. Astronauts will spend most of their time inside a habitat filled with a breathable mixture of oxygen and nitrogen, pretty much like what we have here on Earth. But bringing all that oxygen from home is incredibly challenging due to its mass. However, the water ice buried at AP-8 offers a way to manufacture oxygen right there on site. This is achieved through a process called electrolysis, which is a simple and reliable chemical reaction that's been understood for over 200 years. The process is really quite elegant in its simplicity. Once the ice is melted into liquid water, H2O, an electric current is passed through it. That current breaks the chemical bonds holding the water molecule together, splitting it into its constituent parts: pure hydrogen gas, H2, and pure oxygen gas, O2. The oxygen can then be captured and stored in high-pressure tanks, ready to be bled into the habitat's atmosphere to maintain a breathable environment for the crew. The power for the electrolysis unit would come from the mission's solar arrays, which means astronauts could use sunlight to literally create the air they breathe from the ice in the ground. This capability is not science fiction. NASA has already successfully tested this technology on Mars with the MOXIE experiment aboard the Perseverance rover. MOXIE, which stands for Mars Oxygen In Situ Resource Utilization Experiment, has repeatedly proven that it can pull carbon dioxide from the thin Martian atmosphere and convert it into small quantities of pure oxygen. A future human mission would use a much larger, more efficient system, but one based on electrolysis of water ice. This method is far more productive than pulling oxygen from the thin air. It would allow the crew to generate a surplus of oxygen, ensuring they have robust reserves in case of an emergency. Having the ability to produce their own oxygen provides a mission with a profound level of self-sufficiency and safety. It creates a closed-loop life support system that is not entirely dependent on supplies from Earth. If a leak were to occur in the habitat, the crew could ramp up oxygen production to compensate. They could build up a large stockpile of oxygen, which would be essential for supporting a larger crew on future missions, or for refilling the tanks of their rovers and spacesuits. The simple frozen water at AP-8 is the raw material that allows astronauts to breathe easy, confident in their ability to create a safe and breathable bubble of Earth on the hostile surface of Mars. Perhaps the most ambitious and game-changing use of the water ice at AP-8 is its potential to be converted into rocket propellant. The single biggest challenge of a round-trip human mission to Mars is, honestly, the return journey. The spacecraft that lands on Mars, known as the Mars Ascent Vehicle, or MAV, needs thousands of kilograms of fuel and oxidizer to launch off the Martian surface and get back into orbit to rendezvous with the crew's return vehicle. Launching that return propellant all the way from Earth is incredibly inefficient. It's a bit like carrying all the petrol for a round trip from London to Sydney and back in your car from the very beginning. It makes the initial vehicle enormous and, well, expensive. The water ice at AP-8 provides the raw ingredients for the most powerful and efficient chemical rocket fuel we know, liquid hydrogen and liquid oxygen. As we saw, electrolysis splits water, H2O, into hydrogen, H2, and oxygen, O2. The oxygen serves as the oxidizer, the chemical that allows the fuel to burn. The hydrogen serves as the fuel itself. When combined in a rocket engine and ignited, they react with explosive force, producing a tremendous amount of thrust. The only exhaust product is water vapor, making it a very clean and effective propellant combination. By manufacturing propellant on Mars, we can send the MAV to the surface with empty tanks, saving an enormous amount of mass on the outbound journey. The process would involve a dedicated propellant production plant landed near the habitat at AP-8. This automated facility would work for months or even years before the crew arrives. It would drill for ice, perform electrolysis, and then use cryocoolers to liquefy the resulting oxygen and hydrogen, storing them in super-chilled tanks. By the time the astronauts land, their ride home would already be fully fueled and ready to go. This fueling up on Mars architecture dramatically reduces the cost and complexity of the entire mission campaign. It is the pivotal technology that enables a sustainable program of exploration, rather than just a single, one-off visit. This capability transforms Mars from being just a destination into a true planetary outpost, a base from which we can operate across the solar system. A Mars with its own fueling station becomes a stepping stone to the asteroid belt, or the outer planets. Ships could travel from Earth, refuel at Mars, and then continue their journey outwards. This is the long-term vision that the treasure of AP-8 makes possible. The accessible ice isn't just about survival on Mars, it's about building a robust and sustainable infrastructure for the future of human spaceflight. The path to becoming a multiplanetary species may very well begin with a simple drill bit sinking into the frozen ground of Amazonas Planitia. Selecting a Mars landing site involves comparing numerous potential locations. These sites fall into two categories: locations with geological interest and the polar regions with water ice. AP-8 offers a balance of scientific opportunity, astronaut safety, and feasibility. This balance is vital. The first landing site sets the course for future Mars exploration, We're not just choosing a destination, but a strategy. Comparing sites like Jezero Crater and the polar regions highlights AP-8's compelling features. It balances scientific dreams with engineering realities. AP-8 offers the best chance for a successful first step. Jezero Crater, the current operational area for NASA's Perseverance rover, was chosen because it was once a deep lake with a river delta. Jezero offers an incredible diversity of rocks and ancient sedimentary layers to study. However, what makes a site perfect for a robot does not necessarily make it suitable for humans. The very features that make Jezero so scientifically exciting also make it a hazardous place to land and live because it lacks readily accessible resources. A site like Jezero offers the highest probability of a major near-term astrobiological discovery, but it is resource poor. The Martian poles are rich in water ice, offering a virtually infinite supply. However, this abundance comes with extreme environmental challenges. The long polar winter brings months of darkness, a mission killer for solar-powered outposts. Temperatures plummet to -150 degrees Celsius, straining equipment. A mid-latitude site like AP-8 offers a balance, avoiding the worst polar extremes while still providing subsurface ice and year-round sunlight. This makes it a more practical choice for a first human outpost. When we place AP-8 in context with science-rich sites like Jezero Crater and resource-rich sites like the polar regions, its true advantage becomes clear. It is the quintessential Goldilocks candidate. At AP-8, they can land on one of the safest, flattest surfaces identified on Mars, which also happens to be situated directly on top of a massive, accessible ice sheet, all within a moderate mid-latitude climate. It solves the two biggest problems of a Mars mission: landing safely and finding water, at the same time in the same place. AP-8 offers the science of a living, evolving planet. The advantage of AP-8 is that it systematically reduces risk across multiple fronts, giving the crew the best possible chance to succeed. AP-8 is a location that is safe enough, resource-rich enough, and interesting enough to serve as humanity's first foothold on the Red Planet. Imagine the moment after landing. The priority is confirming the integrity of the habitat. Next, deploy the solar arrays for power. Their boots leave the first footprints in the red dust. The focus shifts to tapping into the hidden treasure. Water ice. The ice is melted, purified, and then subjected to electrolysis. Producing water and breathable oxygen from local resources is a monumental achievement, demonstrating humans can indeed live off the land on another world. With the base established, the primary scientific mission can begin. The main target is the ice sheet, a pristine climate record potentially stretching back millions of years. Drilling transitions from resource gathering to scientific investigation, extracting ice cores for analysis. Inside the lab, astronauts analyze ice cores, identifying layers corresponding to different climatic periods. Trapped dust and gases provide samples of Mars's ancient atmosphere. The most profound question: does the ice contain evidence of life? Finding a single fossilized microbe would be the greatest scientific discovery, proving we're not alone. The crew will also study the local geology, deploy seismometers, and gather climate data. It's a comprehensive investigation into another world, conducted by human hands for the first time. As the mission progresses, the crew's focus shifts outwards to the initial 100-kilometer exploration zone. Using a pressurized rover, astronauts embark on multi-day expeditions, pushing the boundaries of human exploration. These journeys expand our map of Mars and are critical for understanding the regional context of the landing site. This phase is about learning how to be true planetary explorers, developing skills essential for future missions. A key objective is to scout for future landing sites and resources. The first crew are pioneers, paving the way for others. Ultimately, the first crew would be building a legacy, inspiring a new generation. The legacy will be the knowledge that we are no longer a single planet species. The story of Mars exploration is one of relentless progress, from blurry telescopic images to high-definition panoramas. Each mission takes us closer to sending humans to walk on its rusty soil. The identification of AP-8 represents a profound shift, moving the dream of a human mission into achievable planning. AP-8 offers a tangible target for our collective efforts. This location encapsulates the genius of our modern exploratory strategy. It is safe enough to land, resource-rich enough to sustain a crew, and scientifically compelling. It is the smartest choice for our first Martian outpost. The ice beneath AP-8 unlocks a sustainable future on Mars. It is the potential birthplace of a new branch of human civilization. It will be a giant leap for our species as we touch our future on the red planet.